Let's take a look at this one. Kind of like to this problem. A solid is formed by joining two hemispheres to the ends of a right circular cylinder. The total volume of the solid is 12 cubic centimeters. Find the radius of the cylinder that produces the minimum surface area. Right, so I started my diagram there, and I wrote what we wanted to do. We wanted to minimize surface area. Notice that whatever the radius is for the hemispheres, it's the same as the radius for the cylinder, right? So that stays the same. Right? Let's start our primary equation over here, and then we'll go to our secondary equations to help us simplify. All right, so if you want to minimize surface area, that box here. All right, so notice carefully what we have the surface area of. Right? So we have, notice this right here is on the inside. Right? So it helps probably to know the surface area, right, of a sphere and a hemisphere. Right? So for a hemisphere, and we're looking at surface area. I'll just put a little SA there. All right, so the formula for a surface area equation, the formula for the surface area of a sphere, would be, and this is for the hemisphere. Right? So that would be, actually let's do the sphere. So the sphere would be 4 pi r squared. The hemisphere is actually not half. It's half, but then plus that circular base. So the area of a circle is pi r squared. So a hemisphere is 2 pi r squared plus pi r squared, which gives you 3 pi r squared. But that base isn't going to matter, right? It's on the inside. Right? So we're really not going to have to worry about that. Right? That base is on the inside. And so notice that you not only have to take it out of the hemisphere, you're going to have to take that out of a cylinder as well. Right? So it pays to have a drawing there. The surface area here, and so let's go back a little bit. You don't have to write that down. So our surface area, I'll just put S for surface area, is going to be the area of the hemisphere minus the base. Well, if you put the two hemispheres minus the base together, you've got the two top parts, right? You've got this part and this part, you've got a whole sphere. So that's going to be one whole sphere plus your bases on your cylinder are on the inside. So you have the lateral area of the cylinder. My writing's taking up too much space. Right? So surface area of a sphere, like I said, is 4 pi r squared. The lateral area, so surface area formula for a cylinder is 2 pi r squared plus 2 pi r h. Right? So we're just going to need the 2 pi r h part. Right? So what you've got here, you've got the surface area of a sphere, those two hemispheres put together, make it look three-dimensional. And if you unroll it, you've got a rectangle. One dimension is the height. The other one goes around that circle base, and that would be 2 pi r. All right, so those are your two surface areas. All right, so we have, of course, have too many variables here, but never fear. We can reduce those with our secondary equation. I'm going to put the secondary equation over here because it's not going to, the last one, if you were watching example number 3, oh, by the way, I skipped example number 4. I'll do that one in class. Took me a while to write the new and improved primary equation because it took a couple secondary equations. This one is pretty straightforward. We're going to use volume to help us out here. The volume, just add up the two volumes. So the volume is going to be a hemisphere, or half a sphere, plus a cylinder plus another half a sphere. Right, well, if you add a half a sphere, half a sphere and a hemisphere are the same thing. If you add a hemisphere and a hemisphere, or a half a sphere and a half a sphere, you get a whole sphere. Right? So you've got the volume of a sphere plus the volume of a cylinder. Nobody cares that one's on top of the other. Oops, cylinder. We decided to skip the R there. Cylinder. All right, so the volume formula for the sphere is 4/3 pi r cubed. 4/3 pi r cubed. And then the cylinder is the area of the base. So that would be pi r squared times the height. All right, and so we know what the volume has to be. It has to be 12 cubic centimeters. So we'll plug 12 in there. 12 equals 4/3 pi r cubed plus pi r squared h. And we're going to solve for h, because that's the problem we have with our primary equation, is we have too many variables. All right, so we're going to subtract 4/3 pi r cubed. Actually, let's multiply everything by 3 and get rid of the 3 in the denominator. So I should do it to everybody. It's good. And then we won't have to simplify later. All right, so that's going to be 36 equals 4 pi r cubed plus 3 pi r squared h. We'll subtract 4 pi r cubed. So 36 minus 4 pi r cubed would equal 3 pi r squared h. And then just divide both sides by 3 pi r squared, not the h, sorry, 3 pi r squared. And I'm going to simplify that. I'm going to divide each term separately rather than do a quotient rule. So if I divide 36 by 3 pi r squared, right, that would be 12 over pi r squared. And if we divide 4 pi r cubed by 3 pi r squared, right, that's going to be 4/3, just an r. And that's going to equal h. Actually, I changed my mind. Sorry, I forgot that we're just substituting for h. I'm already ready to do a derivative. Well, now I don't have an excuse, because if you heard me earlier, I'm not myself because I'm hungry. Now maybe I'm just tired. All right, I'm going to keep h here as 36 minus 4 pi r cubed. Sorry, I wouldn't simplify until I was ready to take the derivative. Divided by 3 pi r squared. All right, and now we're going to come up to our primary equation, and we're going to replace h with that business there. All right, so, and then we can take the derivative. So we have s equals 4 pi r squared plus, and at that time we will simplify, 2 pi r, and then this is 36 minus 4 pi r cubed divided by 3 pi r squared. All right, so we can do a little simplifying there. And all we did here is we just replaced h. And so that we would only have one variable, just r's. Right? And so the pi will cancel, and this r will cancel. And that one will just become an r. And that's all the canceling we can do. So we'll distribute, simplify, and then take the derivative. So we have s equals 4 pi r squared plus, that's going to be 72 thirds over r, right? So I hope you can follow me there. Each one of these, 36 has to be divided by 3 over r, and I got to multiply by 2. Right, so 72 over 3r minus, right, and so that would be 4/3, but I'm going to multiply by 2, so 8/3, and there's going to be a pi, and r cubed divided by r would be r squared. All right, so there we go. So we'll take the derivative of that, and let's rewrite the negative exponent there. So 4 pi r squared, or rewrite the rational term as a negative exponent, 4 pi r squared plus 72 thirds r to the negative 1 minus 8 thirds pi r squared. We could combine, by the way, that 4 pi r squared and the negative 8 thirds pi r squared. Maybe we should do that. Right? So 4, that's 12 thirds, right? They're exactly the same, so 12 thirds. So 12 thirds minus 8 thirds, that's just going to be 4 thirds. So 4 thirds, positive 4 thirds. 4 thirds pi r squared plus 72 thirds r to the negative 1. Now let's take the derivative. So ds dx, or I guess ds dr, sorry. I'm going to put a little box here. I'll switch colors too. So all we've done so far is this, in this section right here, is just to simplify. All right, so now we'll take the derivative. So ds dr equals, all right, so that's going to be 8 thirds, 8 pi thirds r, reduce that by 1. And then this would be minus, right, because that's r to the negative 1, minus 72 thirds, that's going to be r to the negative 2. So I'll just put r squared down here. All right, so we have, now we can, now we took the derivative, right, now we can set that equal to 0 and solve. So 0 equals 8 thirds pi r minus 72 over 3r squared. Oh, you know, we could reduce that. So why don't we reduce that? 72 is divisible by 3. I don't know why I didn't reduce that earlier. The whole time I could have reduced that. Here, let's just make that a nicer number. Took me that long to figure out. 72 is divisible. So this is 72 divided by 3 would be 24. So that's r to the negative 1. So 24r to the negative 1, and then plus 24 to the r to the negative 1. There we go. All right, and so we'll just change that. No reason to have the 3 there. So that would have been minus 24r squared, r to the negative 2, which is the same as 24 over r squared. All right, so we set it equal to 0, and we'll move that negative term. 24 over r squared equals 8 thirds pi r. All right, and so now we'll cross multiply. You could, by the way, divide in the numerators, divide both sides by 8. But if you don't want to, we'll just cross multiply. So this would be 8r squared equals 24 times 3, which is 72. Divide both sides by 8. R squared is 9. And so that means r equals positive or negative 3. But remember, we have a feasible domain. It has to be greater than 0. All right, so that means r equals 3. And I'm running out of space here a little bit, and so let's go on the next page, and I'll just cut and paste this over, and we'll answer the question. So we have, so far, r equals 3. Right, and we're only looking for the radius, right? So our radius equals 3, but we have to check using our second derivative. All right, so evaluate using second derivative. And that means I need to remember what the first derivative was, which was, before we took the derivative, there it is, it's 8 thirds pi r minus 24 r to the negative 2. So 8/3 pi r minus 24 r to the negative 2. All right? So we'll take the second derivative here. All right, so that's just going to be, so it's going to be d2s over dr2. All right, so derivative of 8/3 pi r is just going to be 8/3 pi, which is a constant. And then this would be plus 72, and then r to the negative 3. All right, so I'm going to simplify that. d2s dr2 as 8/3 pi plus 72 over r cubed. And now we're evaluating it when x is 3, or r is 3. Right? So we have d2s over dr2 for 3 is 8/3 pi plus 72 over r over 3 cubed. Right, so that's going to be 8/3 pi plus, that's 72 divided by 27. We can reduce that, divisible by 9. Right, so that's 8/3 pi plus 8/3. And so this is definitely greater than 0, right? Whatever that is, it's greater than 0. So since f double prime of 3 is greater than 0, r equals 3 is a Rellenkebab. So this is a minimum. You could also, by the way, do a sign chart and also check. And actually, we had done that with the sign chart. That's actually a good way to double check, right? That yours is really a critical point and not a solving error. And I kind of, in interest of time, a little bit on my videos here, neglected to do that. But let's go back and actually do that real quickly. This has been one of the shortest ones. The next one actually is going to be really, really short. So here, r equals 3, right? If we were to do a little sign chart here, so I'll just do that over here. And so we can use 1 and 4. If I plug 1 into the derivative, I'm going to have, well, that'd be 8/3 pi. And that would be minus 24. And so 8/3 pi is greater than 24. So this is going to be positive. Wait, I better double check that. Hopefully we have a sign change here. So, of course the calculator doesn't have one on. So 8 divided by 3. I'll have to approximate. And so it's, yeah, so that's negative. So we're decreasing because we're looking to minimize. We're decreasing. And then if I plug in 4, because 8/3 pi is smaller than 24. What was I thinking? Much smaller than 24. And then if you plug in the 4, that'd be 24 over 16. That's much smaller than 8 pi thirds. This would be positive. Phew. All right, so there's our sign chart. And f prime of x changes. And it's a good idea, by the way, to do both, especially if it's a test. From negative to positive. At x equals 3. So x equals 3 is a relative, I'll put that. X equals 3 is a relative minimum. So really this is a lot like curve sketching, right? Except instead of, we're not really considering the graph as much as we're considering a problem. That's the one I skipped, I'm going to do in class. Our first derivative, our critical point was 6. All right, so if we looked at our first derivative, we'll do a sign chart. I'll do it over here, so I don't have any other space. Oh, sorry, this is the other problem. So sign chart, all right, and so the critical point was 6. If I used 1 and 7, so if I plugged 1 into the derivative, which is somewhere on this page, I'd have 2 minus 72. So negative 70 is definitely a negative number. And if we plugged in, instead of a 7, let's use an 8. Actually, it won't be that. Yeah, either way, it's not going to be very nice. I'll use an 8. So it'd be 2 minus, right, so 72 divided by 8 squared. 72 divided by 64, that's less than 2, right? Just a little bit more than 1. This is going to be positive, right? So same thing. Since f prime of x changes from negative to positive at x equals 6, x equals 6 is a relative minimum. And you might think, the second derivative tells me that. Why would I do it twice? Right? Well, the reason to do it twice is if you've made an error solving for your critical point and it's really not a critical point, your second derivative is just going to tell you if it's concave up or concave down, right? It won't necessarily tell you that, oops, you made a mistake on your derivative. So good idea to check both. And this was the first one we did, so we'll check that one real quickly. What was the critical point? It was x equals 6, right? So if we do a sign chart, maybe over here. Right, so we had 6, we can use 1 and 7, but I need the derivative, which is on the other page. All right, so if I plugged in a 1 into, where's the derivative? Set the derivative equal, there it is, 27 minus 3/4 x squared. All right, so 27 minus 1 is going to be positive. Right? If I plug in a 7, 3/4 of 49, right, is going to be greater than 27. Right, so, and actually I could choose a nicer number that works better with 3/4. How about 8? Right, well, too big because then it won't be outside the feasible domain, whatever that happens to be. But if I used 8, so that'd be 8 squared would be 64. All right, so it'd be negative, it'd be 3 times 16, right? Because 64 divided by 4 would give us 16. So that'd be 27 minus 48, and that would definitely be negative. All right, so this one was positive. Since f prime of x changes from positive to negative at x equals 6, x equals 6 is a relative max. All right, so I would do both. I didn't give you that many problems. Good idea to do both the first and second derivative test. And I'm going to end this podcast, so bye for now.